Hey there, we're on Math 148, section 9.8. Now we're looking at higher order derivatives. And there's essentially two things that are covered in this section, or two concepts that you want to kind of drive home. One is how to take a higher order derivative. How do you take a second derivative, a third derivative? And the second one is what does it mean? So how do you interpret these higher order derivatives? So I'm going to start with this first question, how to do it. I think actually doing the derivatives is not quite as tricky as learning to interpret them. So derivatives, in order to find a higher order derivative, you can just keep going. So that, I know keep going doesn't sound like a very mathematical instruction, but suppose we have some function, f of x is equal to, I'm just going to say x cubed. So the first derivative, which you've gotten pretty comfortable with at this point, is 3x squared. So in order to take the second derivative, you can just do this again. You essentially take the derivative of this function. So the second derivative, let's make that yellow. And look, I made a double prime. That's why I do the primes, because the second derivative is now 2 hash marks. The second derivative, this is the second derivative. You would never write second derivative like this in words. That would be a little bit clunky. You would just write f double prime equals, now we do the derivative of this one. So we're not doing anything new, we're just kind of doing it again. So it's now 6x. So I think of this like crocheting. We're not doing anything really different, we're just doing the same thing over and over and over until we just keep going with the pattern. So you could do this third derivative. Do you guys see the pattern? The third derivative, 1, 2, 3, you take the derivative of the second derivative. That just becomes 6. Yeah, we can go to the fourth derivative. That would be 0. And it's going to be 0 for a long time, because 0, 0, 0, 0. And by the way, when you get to fifth derivative, I think maybe you would just do it like this. I do not think you go like this. 1, 2, 3, 4, 5. That would be silly. So I'm going to do a homework problem that just asks you to find different level derivatives. So question number 9, which says find the third derivative. So we're looking for the third derivative. And here's our function, third der. The function is f of x is equal to 2x to the 9 minus 6x to the 6th. So we're finding the third derivative. You can't, I suppose someone maybe in their mind could go right from 1 to 3, but the more traditional way to do it is just find the first one, the first derivative. So the 9 will jump in front, that's 18, x to the 8th, right, subtract 1, minus, 6 jumps in front, multiplied, 36, x to the 5th, that's the first derivative. It's nice having these colors, I think. Second derivative of x, it should be parentheses, equals 18 times 8, so 18 times 8, you're going to have to use your calculator. I'd use my calculator. I do not have 18 times 8 handy in my head, although I could figure it out. 36 times 5 is 180, x to the 4th, and we're just going to keep going. Third derivative, triple prime. I would say third derivative of x, I wouldn't say triple prime. Somebody might, I suppose. You take 7 times 144, and you get 1008 x to the 6th minus 720 x cubed. Again, I'm sure there's a mathematical shortcut where you could jump right to there, but it's not important to me that you guys have these shortcuts. These were not too many stages to go through. I would just go 1, 2, 3, like that. That is your third derivative. Okay, here's another problem. Question number 23, it's a bit of a tangle. It's a little tricky, but I'm going to do it for you. So the book says f to the 4th, the fourth derivative of x, is equal to x times x plus 1 to the negative 1. Okay, so that's the fourth derivative, and it asks you to find f to the 6th of x. Notice they just said 6, they didn't go 1, 2, 3, 4, 5, 6 like that. Okay, so we have to take the fifth derivative, and then we can take the sixth derivative. So the fifth derivative of x is equal to this little, remember now we have to use our what do you call it, the multiplication rule, the product rule, that's it. So we take the derivative of this one, which is 1, times, this piece stays the same, plus the derivative of this one, negative 1, x plus 1, subtract 1 to the negative 2. Derivative of what's inside is 1. So that was all the derivative of this piece. And now times x. I'm going to simplify this for a second. That's x plus 1 to the negative 1 minus x times x plus 1 to the negative 2. Okay, so now when we take the sixth derivative, this is in theory kind of the last step, right? F to the sixth of x. But it's going to get complicated because we have to do the product rule here again. So the derivative of this piece is negative 1 times x plus 1, subtract 1, to the negative 2 times the derivative of what's inside, which is just 1, minus, okay, I'm going to put a big bracket because this one is a product rule, so I'm going to have to do it twice. So minus 1, so I'm taking the derivative of this piece. 1 is the derivative of that one, of x plus 1 to the negative 2, plus, and now I take x times the derivative of this one. So that's negative 2, the 2 hops in front, x plus 1, subtract 1 there to the negative 3, and times the derivative of what's inside is 1. So the reason I make these big dramatic parentheses is it gets really easy to mess up these parentheses. Negative, when I say mess up the parentheses, I mean mess up your signs as you go through here. So I'm not going to distribute this negative sign yet. I'm going to clean up a little bit. So I have x plus 1 to the negative 2 minus, right, 2 times x plus 1 to the negative 3. Okay, well that seems pretty good, except we have to simplify. So now the next few steps are just going to be simplifying to prove to you that the book was correct. I was not convinced that the book was correct, so I had to simplify to figure it out. So we have negative, I'm going to use a blue pen here, negative x plus 1 to the negative 2 minus negative x plus 1 to the negative 2. So that is negative 2 times x plus 1 to the negative 2. Do you see I'm canceling those two pieces? So minus minus, distribute this out to there, makes that a plus 2x times x plus 1 to the negative 3. Okay, well, if we multiply both sides, I'm trying to do this in a way that doesn't take up so much space, but think about if we multiply this one. Let me write it out like this. This is 2 over x plus 1 squared plus 2x over x plus 1 cubed. And in order to write this in a simpler way, you could multiply this top part and bottom part by x plus 1. So now we can put them all over, that should be to the cubed, not times 3. So now it's all over a common denominator of x plus 1 cubed. Okay, and this becomes up here, kind of right here, this 2 times x plus 1 is 2x plus 2 plus 2x. So the whole thing, oops, sorry, that was a minus 2x. So minus 2 equals negative 2. This is pretty confusing, and I went through that fairly quickly. But this is in fact the answer that the book gets. So taking the sixth derivative, just doing the derivative twice, in this case, it really complicated it. So that's an example of how you power through. Okay, now I'm going to explain what the second derivative and third derivative means. So this was just kind of how to crank through it. Now I'm going to show you some interpretations. So a derivative, the definition of a derivative that may be slowly sticking with you is that it is a rate of change. So the derivative is a rate of change. And here's the most easy to understand example in my opinion. This is example 6. It's on page 614. This is a physics example, and I think it's the easiest to understand because it's something you can physically experience for yourself. So they give you this function, SS is equal to 100t minus 16t squared plus 200. So S is equal to your position, a distance in feet, the distance of some object, or you can think of it as yourself if you're moving, and t is equal to the time. So if you said, what is going to be your distance? Let's say you're in an elevator and you're traveling someplace. What is your distance going up over time? Okay, the first derivative, so s prime of t, is going to be your velocity. This is your speed. Velocity is the rate of change of distance. Rate of change of distance. How quickly are you moving from one place to another place? So imagine yourself on the bottom floor, and then 4 seconds later you are up several hundred feet. What was your rate of change? What was your velocity? Okay, but you can also, so velocity is, it's sort of your speed. There's a subtle difference I don't want to get into. The second derivative is your acceleration. And all of you who have put your foot on the gas know about acceleration, and that is the rate of change of velocity. Rate of change of velocity. How quickly are you changing your velocity? Right? If you're going along at a 20 miles an hour and then you kick it up to 100, that is your acceleration. So let's take the third derivative. The third derivative of the distance function. What is the rate of change of acceleration? Rate of change of acceleration. There is a word for this, and you may not have heard it. But you could imagine if you're with a driver in the car, let's call him a teen driver, and he's accelerating really fast, and then he slows down, and then he accelerates it again. He's constantly gunning it and then letting off the gas. Your rate of change of acceleration, you're going to feel that, and you feel it in a roller coaster. And the word for this is called jerk. It's the rate of change of acceleration, and it's often calculated, I got this from Wikipedia. See, if acceleration can be felt by a body as the force, the object, a jerk, here it's right here, jerk can be felt as the change in pressure. For an example, a passenger in an accelerating vehicle with zero jerk will feel a constant force, whereas positive jerk will feel an increasing force, and negative jerk is decreasing. Applications often used in engineering when building roller coasters. If you think about jerk from outer space, okay, I'm not going to get distracted by that. So you can, the jerk would be, I always think of it in an elevator. If you feel the acceleration change differently, that's the third derivative of distance. What is happening? So some of these problems, they get a little bit wordy. They say, what is the rate of change? That's the first derivative. What is the rate of change of the rate of change? That's the second derivative. But the thing I like about this example is the different rates of change have words that we know. For example, s, the first one is just the distance that you're traveling. The first derivative is your velocity. The second derivative is your acceleration. And the third derivative is your jerk. So now that you understand that, you can understand this really hilarious t-shirt. Don't be a first derivative of acceleration, a jerk. Isn't that awesome? It's so funny. I knew you guys would appreciate that. You were laughing right now. Sort of warned you to get some Kleenex to wipe those tears out of your eye. Maybe I'll get a shirt like that.